So we'll wait for a while. Maybe 1 or 2 minutes. Okay. Yeah, so I have just started. This one. Yeah. So we are getting numbers almost came. Okay, let's continue with this problem. See, in this problem, an alternator with mod E 1 per unit. Alternator with mod E 1 per unit, comma XD equals to 1 per unit. XD equals to 1 per unit. Connected to an infinite bus through a series impedance of Z equals to minus J 1.5 per unit. Minus J 1.5 per unit. The power transfer from alternator to infinite bus is 1 per unit. So simply in the stability analysis, if we said power transfer is 1 per unit, we should say it's a real power transfer, 1 per unit. Okay. What is the stable rotor angle made by alternator with respect to infinite bus? What is the stable rotor angle made by the alternator with respect to infinite bus? That's the question. Okay. So let's see in the solution first. This is alternator. What are the reactance of alternator? You said XD equals to 1 per unit. Means I can say alternator series impedance J1 per unit. Alternator series impedance J1 per unit. And this induced EMF is how much? 1 at an angle delta. 1 at an angle delta. And we have some series impedance like this connected Z value minus J 1.5 per unit. Minus J 1.5 per unit. End infinite bus. And this voltage he said as 1 at an angle 0 degree. That infinite bus voltage he said as 1 at an angle 0 degree. Okay, next thing. Could you please tell me what is the overall impedance of network connecting that generator to infinite bus? What is the overall impedance of the network? That Z equivalent you call if you want. Z equivalent value. So it will come to the minus J 0.5 per unit, right? The Z equivalent value will be equals to minus J 0.5 per unit. Good. Listen. Power flow in the network means you call it is P naught. Present power flow in the network P naught. That value was 1 per unit. Okay. Present power flow. P naught is equals to 1 per unit. What is the power equation? Power equation, if you write P is equals to P maximum sine delta. Power equation P is equals to P maximum sine delta. What is P max equation here? What is P max equation? Can anybody tell me? What is that maximum power transfer equation in this case? P maximum value is nothing but mod E into mod E by equivalent transfer reactance. Equivalent transfer reactance between these two sources. What is E value given? 1. V value 1. Okay. What is X equivalent value? Anybody? What is X equivalent value? Please tell me. Minus 0.5 we should substitute. Okay, including the sign. Including the sign we have to substitute here. Minus 0.5 we have to substitute. Not with J. Abjit and Ashish. Not with the symbol of J. We have to keep only imaginary part of it here. Imaginary part. Imaginary part is how much? Minus 0.5. Okay. So this number will come to be minus 2 per unit. Now you write that power equation simply minus 2 sine delta. Power equation you can write as minus 2 sine delta. Minus 2 sine delta. Okay. Now you assume that initial rotor angle is delta naught. Initial rotor angle is delta naught. Or present rotor angle is. Present rotor angle is delta naught. Rotor angle is equals to delta naught. So at the delta naught angle, if you write this power P naught, it will come to be minus 2 sine delta naught. Na? It will come to be minus 2 sine delta naught. How much is the value of P naught given? How much is the value of P naught given? 1 per unit. 1 is equals to minus 2 sine delta naught we should write. Okay. Then how much is the value of sine delta naught here? 1 by minus 2 means in the sense it is minus 0.5. Sine delta naught value was. Sir, in this problem, resistance will be there means how will be Z equivalent? See, actually at the time you get the R plus Jx or R minus Jx form, right? Govind Vikas. If you have resistance, it will be coming in the form of R plus Jx or R minus Jx. At that time, P maximum equation means we should use the ABCD equation. P maximum equation means we should use the ABCD equation. Getting me? Right? Yeah, you find out ABCD parameters. Substitute ABCD parameters in the Pmax equation. That will give. Let's move. Sine delta naught. How much is delta naught value? Tell me please. How much is this angle delta naught? Delta naught. Two options you get. One option minus 30 degree. Okay. One option will be minus 30 degree. Another option, anybody? Any other option we get other than minus 30? Minus 150 is another option, right? Minus 150 degrees is another option. Just observe here. Sine 150 is positive. Sine 150 is a positive value, but I need negative value, right? So I should take sine of minus 150 degree. Get this minus 0.5. So delta naught, two options here. One is minus 30 degree, another one is minus 150 degree. Which option we have in the ABCD given? Both. Minus 150 you have, as well as minus 30 also we have. And we have to choose one among these two. One among these two. See, actually, he said, what is the stable rotor angle? Stable rotor angle made by the alternator with respect to infinite bus. Stable rotor angle made by the alternator with respect to infinite bus we have to get. At which angle the system will be stable? That's the question. At which angle the system will be stable? It's not synchronous motor, Kavya. It's not synchronous motor. Okay? Tell me please. Which one? Which angle I have to consider among these two? Is it minus 30 or minus 150? Look here. Tell me, how to decide whether the system is stable or unstable at a given angle? How to decide whether the system is stable or unstable at a given angle? Anybody? We have to calculate the slope. And after calculating slope, at whichever the angle you get the positive slope, that angle we will say as a stable angle. Right? What is the slope of the curve? What's the slope of the curve? Formula for the slope. dP by d delta is a slope. And we can write it as this P minus 2 sine delta we have to differentiate. So it will come minus 2 cos delta. Minus 2 sine delta we have to differentiate. It will come to be minus 2 cos delta. Now, this value we have to calculate at minus 30 degree as well as at minus 150 degree. So case 1. At delta naught equals to minus 30 degrees. What is the slope? dP by d delta equals to minus 2 cos of minus 30. Right? So it will come to be minus 1.732. Cos of minus 30 is plus cos 30. Cos of minus 30 is plus cos 30. Cos 30 is root 3 by 2. 2 will be cancelled. Minus root 3. Minus 1.732. Less than 0. Less than 0. Means what is that minus 30 degree? At that minus 30 degree, whether the system is stable or unstable. Whether the system is stable or unstable. Tell me please. At minus 30 degree, the system will be unstable. Why? In the sense we are getting this slope as negative. So this delta naught equals to minus 30 degree is an unstable rotor angle. Unstable rotor angle. Rotor angle. Okay. Yeah. Next one. Second one. At 150 degree negative, minus 150 degree negative, and what is that dp by d delta value? dp by d delta will be minus 2 cos of minus 150 degrees. Minus 2 cos of minus 150 degree. And if you calculate this one, you will get this value plus 1.732. Plus 1.732, and it will be greater than 0. Means at minus 150 degree, we get the positive slope. So I can say this delta naught minus 150 degree will be the stable rotor angle of the system. Stable rotor angle of the system. Okay, so what's your option now? What's your option? That will be minus 150 degree, means correct option will be B here. Correct answer will be B. Stable rotor angle we have to take. Option. Yeah. Now, many of you are having a doubt like this now. Sir, why that minus 90 to plus 90 degree? You said earlier in that range of angles the system is stable. Why you are unable to adopt that statement here? See, whether the system is stable or unstable, it is not depending on the angle, strictly speaking. It will be decided by slope of the curve. Slope of what curve? Power angle curve. You draw the power angle curve and check it. You draw the power angle curve and check it. What is the power equation we have? What is the power equation we have? P is equals to minus 2 sine delta, na? Minus 2 sine delta. And you have to plot that curve. Plot that curve. Please plot that curve once. Plot that curve. I will come back within 1 minute. Plot that sinusoidal curve. I will come back within 1 minute. So if you plot this curve, if you plot the sinusoidal curve, it will come like this. It's a delta axis and it's a power axis. I'm showing delta axis and power axis like this. And it's a minus 2 sine delta curve. Na? Minus 2 sine delta curve means it's an inverted cosine. It will be inverted cosine. Sorry, inverted sine. Inverted sine. So you will get so you are going to get the curve in this manner. And what's the peak of that curve? Here it is plus 2 and here it will be minus 2. Plus 2 and minus 2. And this is the angle at which we are getting the positive value as minus 90 degree. And this is the angle at which we are getting the negative peak value as plus 90. Yeah, how you are getting these angles as minus 150 and minus 30? You have to apply sine inverse. That's it. Very simple mathematical thing. Sine inverse of minus 0.5 will give the angles to you. You get many angles. I've taken only two angles here, minus 30 degree and minus 150. Let me proceed. Okay, so it's a power angle curve for you. It's a power angle curve. Yeah, kindly observe. What is the power flow in the network you have? What's the power flow in the network? Plus 1 per unit. Plus 1 per unit in the sense, this is the value plus 1 per unit. So with respect to the plus 1 per unit, if you see on this curve, we get 2 points. Two intersection points we are going to get. Okay, the first intersection point, angle will be minus 30 degree you got. Second intersection point angle will be minus 150 degrees we are going to get. Tell me, very simple. At what angle we have a positive slope? At what angle we have the positive slope? Observe here. At this point, we have a rising curve. So at minus 150 degree, we have a positive slope. At minus 30 degree, we have a downfall curve. So we have a negative slope here. By that way, we are saying minus 150 degree angle is a stable rotor angle. Minus 30 degree is a unstable equilibrium angle. Okay? I think all of you getting this one. Yeah, good. Next one. Let me explain again this problem for you. Very simple thing. You have to observe the difference between the previous problems and this problem. After taking up overall equivalent impedance, I am observing that is minus j0.5. Is the transfer impedance is capacitive in nature. That is one observation. Transfer impedance is in capacitive nature. But still I am following same formula for P maximum. EV by X equivalent. X equivalent value we have to keep minus 0.5. If you keep that maximum power transfer capacity of this network is minus 2. Okay. And if you go with the power equation, that is like minus 2 sine delta. But the present power flow is 1 per unit. By making the power minus 2 sine delta naught equal to 1, we have to calculate the value of delta naught. We say we have two options here. One is minus 30 degree, other one will be minus 150 degree. If you want to write some more options, I can write one more angle delta naught as plus 210 degree. No issue with that. Plus 210 degree. That's also one of the options. We have it in the options A, B, C, D. No, 210 degree we don't have in the options. That's okay. 210 degree. At 210 degree, if you find out the slope, you may get positive. Means I can say minus 30 degree is an unstable rotor angle. Minus 150 is a stable rotor angle. 210 degree will be again stable rotor angle. Again, stable rotor angle. So these two will be stable rotor angles. One among the two is available in the option. So we should go with minus 150 degrees. Okay, yeah. So please wait again for one more minute. I will come back and I will tell you the difference between this curve and previous power angle curve what we have drawn. Simple. So I have resumed. So why the Pmax is coming negative means that is obviously due to capacitive transfer reactance. So this curve we are going to get if transfer reactance is capacitive, this type of curve you are going to get. But earlier curves which we have discussed, maybe this one, this power angle curve will come for if the transfer reactance is in the inductive nature. This is if transfer reactance is inductive nature. Inductive nature. Okay. You please tell me now. Please tell me. Who is going to decide? Who is going to decide the angle? Who is going to decide the stable operating angle and all? Tell me all of you. Very simple question. Very simple question. Come out of ambiguities and the things what you have learned earlier. Come out of all the things. Just tell me. Who is going to say about the angle? What angle is a stable operating angle? What angle is an unstable operating angle? It will be definitely depends upon the network. Parameters of the network what you have between the generator and the infinite bus. This is going to decide what is a stable operating angle and what is an unstable operating angle. Or at what angle the slope is positive, at what angle the slope is negative. Following all of you? Right. Fine. So anyhow, practical power system network, what we say, practical power system network, what we say. In that case, transfer reactance will be inductive in nature only. Transfer reactance will be in the inductive nature. That's why the people will say leisurely between minus 90 to plus 90 degree, we have a positive slope and the system is stable. Conditions apply. What is that condition? Transfer reactance is in inductive nature. If transfer reactance is coming in capacitive nature, we get some different result in this manner. Okay, fine. Next thing. Let's think about what are the methods to improve the steady state stability of the system. Methods to improve steady state stability of the system. Methods to improve the steady state stability of the system. Yeah. See, I feel only one method we have to improve the steady state stability. I feel that we have only one method to improve the steady state stability. That is making the synchronizing power coefficient at the present operating condition as high as possible. Okay, so dP by d delta value at the angle delta naught, which is nothing but P maximum cos delta naught. It should be maintained as high as possible. Maintained as high as possible. As possible. That's it. Right. So in that, first one I'm going to tell you. To maintain that dP by d delta, P maximum cos delta naught as very, very high. One option is maintain cos delta naught value very high. Maintaining cos delta naught very high means delta naught must be low. Okay, so delta naught must be low in the sense, definitely we can say loading on the system should be maintained as very less. Means if the system is having a light loading condition, lightly loaded operation, at that time, the system stability will be very high. Okay, so first one we can say maintain loading on the system as very low, loading on system as very low, that implies delta naught will be less definitely, cos delta naught will be high, and you can say dP by d delta will be high, and system stability will be definitely high, we can say. So this is option one. Second option, to have high value of dP by d delta, maintain high value of P maximum. Maintain high value of P maximum. What is the P maximum equation? What is the P maximum equation? Mod E into mod V by X equivalent. Mod E into mod V by X equivalent. Means that method, what I am going to say is maintain higher excitation for the alternator, maintain higher excitation for the synchronous machines, maybe alternator, motor, whatever it is. Maintain higher excitation and operate the system at higher and higher operating voltages. That will make the P maximum value high, and synchronizing power coefficient is also high, and system stability will be definitely improved. Okay, so in the second method, I'm going to say, second method, maintain over excitations for synchronous machines. For the synchronous machines, you have to maintain over excitations. That's one thing. And next option, operate system at higher voltages. Higher voltages. Operate the system at higher voltages. That will also lead to maintain the P maximum value high. And the next method I am saying you, maintain the equivalent reactance of network as low. Means transfer reactance, if you make low, P maximum value will definitely increase. Right? Reduce the equivalent transfer reactance value. Reduce the equivalent transfer reactance value. How to reduce that equivalent transfer reactance? What are the various techniques we have to reduce the equivalent transfer reactance? Techniques to reduce the equivalent reactance. One method is adding series capacitor, or you say sometimes providing series compensation. Providing series compensation is nothing but adding series capacitor, right? Keeping series capacitors, keeping series capacitors is one option. And next option I'm saying, using double circuit line, bundle conductors, parallel transmission lines. These things will come in TNT. Okay, using double circuit lines, bundle conductors, and parallel transmission lines. Will make that X equivalent value low. Okay, yeah. So these are some techniques. There is one more technique in order to increase the value of maximum power transfer capacity that I'm saying as a fourth one, that is midpoint compensation technique. Midpoint compensation technique. Midpoint compensation technique. So I will try to discuss about this midpoint compensation technique in a brief manner. First point I'm explaining, Ankur. First point, what I said. Very simple, Ankur. If you are maintaining loading on the system as very less, if the loading on the system is very less, operating angle will be less. Delta naught will be less. Means if the operating angle is low, delta naught is low, cos delta naught will be high, right? If cos delta naught is high, then definitely dB by d delta will be high. Right? So in that sense, definitely system stability can be improved if you are maintaining loading on the system as less. Means if you operate the system at lightly loaded condition. Okay. Yeah, loading is defined by load angle. Yes. How much power flow we have? Obviously, that what we call that power angle can be saying same thing, right? Power angle can be saying same thing. But efficiency will be less, no sir. Efficiency, it will be high only, Shamala. It won't be low. The second point, what I am saying is simple. Second point. See, if you are maintaining higher excitations for machines, in the sense, excitation EMF E will be high. If excitation EMF E is high, maximum power transfer will be greater, right? Then definitely system stability is increasing. Excitation is more means maximum power transfer capacity is more. System stability will be more. Okay, next thing. Let me continue with respect to midpoint compensation little bit. midpoint compensation technique. Midpoint compensation technique. So it is nothing but simply keeping some compensator. Maybe you can say reactive power compensator. Reactive power compensator. Yeah, we are improving triple not rigidity factor, sir. So why first point? See, you are not improving the triple. What you have understood, Pramod now? What you have understood from the first one? What I said here? Huh? What I said here? To maintain good stability, what I said? This whole Pmax into cos delta naught should be maintained as high as possible. See, all the time, Pramod, you should not say improving steady state stability means increasing P maximum. That's not only one option. The other option is also there, reducing the, increasing the value of cos delta naught, right? Improving the steady state stability of system means improving the value of means increasing the value of dp by d delta. Increasing the value of dp by d delta. Clear? Yeah, let's move. Let's move. Midpoint compensation technique. See, in this technique, we are going to keep some separate reactive power compensator. Separate reactive power compensator at the midpoint of the transmission line. Midpoint of the transmission line. So I will do like this. First, without midpoint compensation, I will discuss the thing. Second case, with midpoint compensation, I will discuss it. Okay. First case, I am taking the without midpoint compensation. Midpoint compensation. So this is some source you have, ideal voltage source you take, connected to some line, and then at the end you have an infinite bus. Infinite bus. And this is the voltage mod V1 at an angle delta. And this is a voltage mod V2 at an angle 0 degree. Mod V1 at an angle delta, and then we have mod V2 at an angle 0 degree. Thought that improving the value of triple cell means one thing you try to get the difference between steady state stability limit and steady state stability. Steady state stability limit is P maximum. Improving steady state stability means increasing the value of dp by d delta. In that, P max increment is one of the options. Cos delta naught increment is also another option, right? Yeah. Look here. So this impedance of the line is simply Jx. No resistance here. No resistance. Only reactance we have for the network. And what is the expression of the electrical power flow in this one? P. Simply like P. What is the expression for the electrical power flow? Mod V1 mod V2 by X into sine of delta minus 0. That means it is sine delta. Okay, V1, V2 by X into sine delta. And I'm making one small assumption, which will be helpful after keeping midpoint compensation also. Mod V1, mod V2 values we are making as equal. Okay, let's mod V1 and mod V2 values as equal. Then what is the power flow here? Mod V square by X into sine delta. Mod V square by X into sine delta. And whatever the value mod V square by X we have, that we are going to name as maximum power transfer capacity of network without keeping the midpoint compensation. Okay, so maximum power transfer capacity of network is mod V square by X. Mod V square by X is a maximum power transfer capacity of network that we are calling as P maximum 1. Okay, let's move to second case. We are keeping some midpoint compensation at midpoint of the line. Okay, with the midpoint compensation. Midpoint compensation. So same network, let me repeat in this. Same network we are repeating. Okay. And I will be keeping that compensator exactly at the midpoint. And I will be dividing this line into two parts, x by 2, x by 2. x by 2, and this is a midpoint. Is half impedance, and this is the remaining half impedance, and this is the midpoint compensator we have connected. Midpoint compensator we have connected. And the type of this compensator, type of this midpoint compensator, I'm going to tell it as STATCOM. I'm calling this midpoint compensator as STATCOM. It's a static synchronous compensator. It's going to be taken as static synchronous compensator. STATCOM. Static synchronous compensator. See, it is an equivalent to synchronous machine or synchronous motor you are saying. It is an equivalent of synchronous motor operating under no load condition. It's an equivalent to synchronous motor operating under no load condition. How you represent the synchronous motor in the equivalent circuit? Voltage source in series with the reactance, right? In the similar manner, we can represent this STATCOM also in the equivalent circuit, right? It's an equivalent to no load operating synchronous motor. Okay, next let me show the change here. It is V only, it's not V1. It's also V, it's not V2. Both voltages are equal, we have taken earlier, right? So it is mod V at an angle delta and it's mod V at an angle 0 degrees here. Okay, next thing. This midpoint will have some voltage mod Vm at an angle theta. That midpoint might be having an angle, might be having a voltage of mod Vm at an angle theta. And this STATCOM what we have here, it is not going to consume any real power. So it's a lossless equipment we have at the beginning. Lossless equipment. More real power consumption. Next thing. See, we have some real power flow in this part of network, as well as we have some real power flow in this part of network. And STATCOM is completely lossless, we are saying. And simple. Write the equation for the P in the first part. P1 was. Take the P2. Write the equation for P2. And both powers are equal, right? Both powers are exactly equal. Based on that, you try to get the value of theta. Means what is the midpoint voltage angle? Midpoint voltage angle that we are interested to know by equating the P1 and P2. Okay, right. So I'll show in the next slide. Equation for P1 is simple. Mod Vm by x by 2. That is the P maximum of that part of network. Mod V into mod Vm by x by 2. Multiplied with what you should say? Sine of delta minus theta. Sine of delta minus theta. And what is the equation for P2? What is the equation for P2 here? P2, you kindly observe that P2. How much? What is that? P2. Mod Vm, mod V by x by 2 into sine of theta minus 0. Mod Vm, mod V by x by 2 into sine of theta minus 0. See, if you equate these two, P1 and P2 values are equal, means this maximum values will be cancelled out, right? Vm by x by 2, Vm by x by 2 will be cancelled out. The conclusion what you can get is sine of delta minus theta is equals to sine theta. Sine of delta minus theta is equals to sine theta. And if you write from this, you can get delta minus theta value was theta, means 2 theta equals to delta. And how much is theta here? Delta by 2 you can see. So that midpoint voltage angle is delta by 2. Midpoint voltage angle is delta by 2. Clear? Getting all of you? Right. So this we can rewrite as mod Vm and angle is delta by 2. Mod Vm and that angle is delta by 2. Yes. Right. Next thing. Let us redraw this network a little bit. I will explain about this network. Redraw this network a little bit. So this is your generator. So it's a neutral point actually. It's a neutral point. Per phase model you feel. And it is x by 2 reactance. Okay, midpoint. The remaining x by 2 here. And this side again you have one more voltage source, that is the infinite bus voltage source. Else you keep simply infinite bus. It's the voltage source that you have to remember. Mod V at an angle 0. This is mod V at an angle delta. And the midpoint statcom here, na? Midpoint statcom, that is going to be represented with some reactance and voltage source. With some reactance and voltage source. And that reactance value was very, very low. This reactance value was very, very low generally. Excess I can. That is the reactance of statcom. Reactance of statcom, internal reactance. And how statcom will have reactance means maybe you have an interconnecting transformer, coupling transformer. That will have some reactance, right? That is considered as excess here, which is very, very low number. Very, very low number. Okay. And we have some internal voltage here. We have some internal voltage for this one. Look Alafi. Look Alafi. Very simple, very simple. Don't confuse, don't confuse. This is the midpoint of network, right? Midpoint of the network. See, with respect to midpoint of network, I want to redraw this portion of network. This portion of network into Thevenin equivalent model. Remaining part what you have Jx by 2 and infinite bus, I will feel as a load. I will feel this Jx by 2 and mod V at an angle infinite bus, that as a load. And only this part of network we are going to consider now. Only this part of network. And this part of network we want to replace with a single voltage source in series with the reactance. Single voltage source in series with the reactance. Very simple, very simple. Kindly observe, kindly observe. What is this source voltage you can experience? As a excess is very, very low number. The excess value was very, very low number. This voltage will be approximately mod Vm at an angle delta by 2 only. How many of you will accept it? Please tell me. I am repeating the statement, kindly observe. Excess is very, very low number. As I am saying, excess is very low number. Whatever the midpoint voltage we have, the same voltage will appear for the source also. Same voltage will appear at the source also. Yes or no? That's excess can be neglected, right? Excess can be neglected. As it is very close to 0, then obviously midpoint voltage what you have, that will appear for the source. Yeah, good. Right. Now, if you find Thevenin equivalent reactance with respect to midpoint, what is the Thevenin equivalent reactance value? Thevenin equivalent reactance is nothing but x by 2 in parallel with xs now. X by 2 in parallel with xs. But you said xs is very, very low number. If that is the case, this number might be approximated close to 0. That number might be approximated very close to 0. Are you understanding this one now? X by 2 in parallel with xs to find out the x Thevenin value, and xs is very low means x Thevenin will be very close to 0. And what is the V Thevenin value? V Thevenin is nothing but midpoint voltage only. V Thevenin value is nothing but the midpoint voltage value only. Okay. Now, if you redraw this whole network into its Thevenin equivalent model, in the next slide I am going to show. Next slide. Please complete it quickly. I will show in the next slide. Simple. That Thevenin voltage source I will keep as mod Vm at an angle delta by 2. Thevenin reactance 0. Remove it. And next load will be Jx by 2 associating infinite bus. Yeah. So this is V Thevenin, which is mod Vm at an angle delta by 2, and x Thevenin is 0, Okay, and you have the remaining part of network. It's the midpoint. It is j x by 2, and this is the infinite bus. Infinite bus, which is mod v at an angle 0 degree. Mod v at an angle 0 degree. Now, can anybody tell what is a powerful equation from this network? Can anybody tell what is a powerful equation from this network? Power flow equation from this network. P is equals to what you can say, mod Vm into mod V by x by 2. Mod Vm into mod V by x by 2 into sine of delta by 2 minus 0. Sine of delta by 2 minus 0. This is a power equation, what we can say. So this is nothing but 2 times of Vm V by x into sine delta by 2. 2 times of Vm V by x into sine delta by 2. And if you are saying that this Vm value is also equals to mod V. If you are maintaining that if mod Vm value is also equals to mod V, then how is the power equation to you? 2 times of mod V square by x into sine delta by 2. 2 times of mod V square by x into sine delta by 2. Then what is the Pmax of this network, I can say? What is the Pmax of the resultant network, I can say, after keeping midpoint compensation? That is 2 times of V square by x. Right. So with midpoint compensation, maximum power transfer capacity will be 2 times of mod V square by x. And already we have the P maximum 1, right? Already we have the P maximum 1. How much is that P maximum 1? Mod V square by x. Now, P maximum 1 value was mod V square by x. So finally, what you can write from this is P maximum 2 is double the value of P maximum 1. Double the value of P maximum 1. Right? So maximum power transfer capacity was almost doubled. Almost doubled. Right? That implies maximum power transfer capacity value was increased, then definitely stability of the system is going to be increased. Stability of the system will be increased. Maximum power transfer capacity value was increased, then definitely we can say stability of the system is going to be. Angle decrease definitely in the edge. Yes, angle will decrease. Next thing. See, in the examination, anywhere in the exam, if you find simply this type of model, right? Find this type of model anywhere in the examination. Simple, very simple comment I am making now. So this point voltage already we calculated as mod Vm at an angle delta by 2. And this is some real power flow P1. And this is some real power flow P2. And this is a STATCOM lossless. Midpoint compensated. Yeah, please kindly listen my words. What is P maximum of this network? What is P maximum of this network? Anybody? Delta by 2. So delta by 2 become 1. Become 1 means delta value 180 degree as it is increasing now. Yes, correct. Means we have a limit up to 180 degree now. We have a limit up to 180 degree. Earlier means without midpoint compensation, you might be having power angle curve, something like this. without midpoint compensation, you might be having a power angle curve in this manner. This manner. It's 180 degree without midpoint compensation. After providing midpoint compensation, your power angle curve will come like this. Okay, so 180 degree is an angle at which we are going to touch the maximum power transfer. This is with midpoint compensation, power angle curve with midpoint compensation. And this blue color curve, what we have shown here is, this is without midpoint compensation. Midpoint compensation. Have you understood this one? Clear? Okay, listen to me. If anybody asks you, what is maximum power transfer capacity of this network? Maximum power transfer capacity of this network. Then what you should answer is, you take the first part of network up to compensation location. What is the P maximum value of this? Mod V into mod Vm by X by 2. What is the P maximum of second part of network? What is P maximum of second part of network now? Tell me, what is P max of this one? It will be mod Vm into mod V by X by 2. Both are equal, right? Both are exactly equal. Both are exactly equal. What is an x-axis? Obviously, it is angle, right? Delta, and this is power. Tell me please. Two parts of network we have with respect to midpoint compensation. Left side, 1 P maximum. Right side, 1 P maximum. Which P maximum we have to consider as P max of whole network? Which P maximum we should consider as P max of the whole network? Anybody? Please tell me. Please tell me. Which P maximum we should consider as P maximum of whole network? Both are equal. Not addition. It's not addition. Please listen. Both are equal. Both are equal means anyone we have to consider. Both are equal means anyone we have to consider. So I can write simply maximum power transfer capacity of this network is mod V into mod Vm by half of the line TM. Any one value we have to consider. But some cases, listen please, some cases, one value may be low, other value may be high. One part value may be low, other part value may be high. Which value we have to consider now? Is it low value or high value? Which value we have to consider? Low value we have to consider as a P maximum. Low value we should consider as P maximum, not the high value. I will try to tell you the reason if you move into the problem. If I move into the problem, I will try to tell you the reason. Bhavani, kindly understand what I am saying further. Yeah. Let us take one small problem on this one. Very simple problem I am taking up. It is a problem asked in previous IES examination. It's a direct question to you. Direct question. What's your answer here? Tell me please. In the transmission line, the midpoint voltage is maintained as V by keeping a compensating device as shown in the circuit below. As shown in the circuit below. Okay. What is the real power flow through the line? What is the expression for real power flow through the line? What is it? What's your option here? D. Yes or no? Answer will be D. That's what we have derived just now. Okay. So it will be simply Vm into V magnitude of Vm, magnitude of V by X by 2 into sine of delta by 2 minus 0. They have not given delta by 2 here. We know from previous discussion, we know it is delta by 2. Okay. So as Vm wants to equals to V, he said, so it will be 2 times of V square by X into sine delta by 2 we have to take. Yeah. Next one. Next question. Observe here. It's a question asked in GATE examination. Previous GATE examination question. Both of this question. Get 2000 examination question it is. So, a transmission line has equal voltages at both ends. Sending end side, receiving end side, if you want, right? Both sides you have equal voltages. Maintained as constant by two voltage sources. A third source means voltage source. Third voltage source is to be provided to maintain constant voltage equal to the end voltage. For example, if you keep end voltage as V, wherever you keep the source, that point voltage also equals to V only in magnitude. Okay. At either the midpoint of the line or at 75% of distances from sending end, then the maximum power transfer capabilities of the line in original case and the other two cases respectively will be the following ratios. Right? Understand the problem. Try to understand the problem. It's a previous GATE examination question. Observe, I'm showing in the next slide. First of all, the case one, original case, without that third source, without keeping that third source, in the original case, we have two sources like this, connected by one line. This source voltage is mod B, reactance of network is X. What is Pmax of this network? You call it as P maximum 1. What is it? Mod V square by X, na? P maximum 1 value will be mod V square by X. Simple. Second one. Observe, I am looking at the second one. Look here. A third source is provided to maintain constant voltage at either the midpoint of line or at 75% distances. Means in the second case, I should take a third source at the midpoint. And you have to calculate Pmax of the network. Okay. In the third case, I will keep that source at 75% of the distance, and I have to calculate the Pmax. Look, second case. I am showing network like this, original network first. Both sides you have constant voltage sources, mod V, and total reactance is X for the line. We will take care of that. But at the midpoint exactly, we are keeping one more source to maintain this voltage as mod V. At the midpoint of that line, we are keeping one more source to maintain voltage as mod V. Okay. And what is this reactance value? X by 2. What is this reactance value? X by 2. And here we have two parts of network. We should find out Pmax of part 1, Pmax of part 2. What is Pmax of this part? First part Pmax is mod V square by X by 2, means it is 2 times of mod V square by X. And what is the second part Pmax now? That is mod V square by X by 2. So it will be 2 mod V square by X. Both are equal, right? Both are equal. Then what is the P maximum of the network you should consider? What is P maximum of this network you have to consider in the case 2? It will be any one of these two numbers. So it will come to be 2 times of V square by X. 2 times of V square by X. In the next case, they want to keep the source at 75% distance. Okay, so I am showing the third case now. This is your original network first. And this is mod V voltage, and this is also mod V voltage. And I'm showing one source here at this point, 75% distance. And this voltage is mod V, that voltage is mod V. And you know, this reactance will come 3x by 4, and this reactance will come x by 4. Vx by 4, x by 4 are the reactances. Tell me please, what is Pmax of this portion? Right. Mod V by 3x by 4 means it's 4 by 3 times mod V square by x. 4 by 3 times of mod V square by x. What is Pmax of next portion? Mod V by x by 4. How much is this number? 4 times mod v square by x. 4 times of mod v square by x. Which p maximum we should consider among these two? Which p maximum we have to consider among these two? Tell me please. First one or second one? First p maximum or second p maximum? Which one? Whichever is lower, not the first one, not the okay, first one. Whichever is lower, that we have to consider. Why? Why I have to consider the first one only? Why can't we consider the second one? Why we have to consider only first one? Why can't it be second one? Anybody tell me please? Tell me please. After saying this term, which p maximum we have to consider? I asked this question to one of the students. The student answered me like this. You tell me, is it a proper answer or not? Is it a proper answer or not? Please check what I am saying. Sir, in the first case, you said 4 by 3 times of v square by x, sir. Second case, you said 4 times of v square by x, sir. How the power will be increased from 4 by 3 v square by x to 4 times of v square by x, sir? How power is going to be increased? Power flow is going to be increased from one side to other side, sir. So whichever is lower value, that we have to take. Is it a proper reason? Is it a proper reason to say? Understanding what I am saying? Yeah. Is it a proper reason? First side we have a low power flow. Second side we have a high power flow. Who is giving that extra power flow there? Second side is also carrying same power flow. That's not the thing. What I will tell is, listen. Okay. Somebody is saying correct answers only. Just listen. What is the necessity of calculating P maximum? That you tell me first. Why? Why I have to calculate P max? Why I have to calculate the steady state stability limit? Why? What is the reason? Tell me please. Why? Why in the sense? Based on this value only, we are going to keep the loading on the system. Yes or no? Based on the value of P maximum only, we are going to keep the loading on the system such that the system is going to be maintained in the stable mode. For example, if you are selecting this P maximum for loading on the system, if you are selecting this second P maximum, 4 times of v square by x to keep loading on the system, I can keep 3 times of v square by x as a load, right? Getting what I am saying you. So in that situation, if you keep loading on the system based on this number, definitely the power flow in the network may be higher than the first P maximum. If it is higher than the first P maximum, system will lose the synchronism. Are we getting it or not? Don't know. Very simple thing. For example, if you are keeping loading based on the second value is a very high value. If you are keeping on that one, whatever the power flow you are deciding that may be higher than this first number, right? Then the system will lose the synchronism. That's the issue. So if you choose a first number itself, how synchronism lost means it has been increased. It means it is crossed this P maximum value. For example, you take some numbers if you want, Pujar, you want to take some numbers, I'll say it's 4 by 0.5, say 8, this number, 8. And this is 8 by 3. 8 by 3 means how much? Or is better, I'll say this number is 9. This number is 9 I got. This number, it will be 9 by 3 means 3. So if you keep the loading based on 9 per unit power, I can keep 8 per unit, right? I can keep 7 per unit. I can keep 6 per unit. That number, what you are saying now, is higher than 3 per unit. So definitely system will lose the synchronism. See, if you keep the same loading based on 3 per unit means you should select the number below 3 per unit. If you select below 3 per unit, obviously it will be lower than 9 per unit also. Then system will be well stable. Okay, so whichever is lower among the two, that we have to select. So I can say from these two, maximum power transfer capacity by keeping source at 75% length will be 4 by 3 times of mod v square by x. Mod v square by x. This value we have to select. This is a lower value. Okay, now very simple question to you. Very simple question to you. By this way, you get some clarity regarding this one. We have a compensator, maybe voltage source, as you said in the problem, compensator. If I keep that one at 25% length, 25% length, you will get some P maximum. If you keep that one at the midpoint, you get some P maximum. If you keep that one at 75% length, you get some P maximum. At what location of compensator placement you are getting highest P maximum? Compensator, StatCom, you can keep at 25% length, 10% length, 50% length, 70% length, 75%, 80%, wherever you want, you can keep. Wherever you want, you can keep. But which location of placement is giving highest value of P maximum? Which location of placement is giving highest value of P maximum? Midpoint, 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 midpoint. That's the reason why this midpoint compensation is very famous in textbooks. Because midpoint compensation itself will give the highest to maximum power transfer capacity compared to any other location placement. That's it. Simple reason. Okay. Yeah. Anyhow, in the question, what he asked me is this ratio Pmax 1, Pmax 2, Pmax 3 ratio. Pmax 1 mod V square by x. Pmax 2 2 times of mod V square by x. Pmax 3 4 by 3 mod V square by x. And if you do the cancellation, 1 is to 2 is to 4 by 3. 1 is to 2 is to 4 by 3. Cross check the options here. 1 is to 2 is to 1 by 0.75. Option B is a correct one. Option B is a correct one. Okay. Means if you want, you write this is 1 is to 2 is to 1 by 0.75. 1 by 0.75. Okay. Yes, correct, Arvind. Arvind was, that's correct what he said. Yeah. So we stop the class at this point. Tomorrow class we will be starting with the transient stability analysis. Tomorrow class we will be starting with transient stability analysis. If anybody have doubts, you can raise your hands. First, let me make all the hands low. I'm making all the hands low first. Kindly wait. Please raise your hands now. Please raise your hands. Vashri.
Sir, 59F low rigidity factor and చెప్పారు sir అంటే
strength rigidity means what? What is the dictionary meaning of rigidity?
Sir, I searched Google. It is showing like constant pressure is between constant pressure and the tight pressure.
Means, listen, rigid means strong.
Sir?
Strong. Rigid means strong.
Strong. Okay.
High strength.
Okay. Sir.
Okay. How far your system is having a strength to accept the disturbance.
Okay, sir.
That we are saying as rigidity factor.
Okay. So power factor, something you wrote, na sir. One more. Once open the 58 of 59F. Electrical stiffness also.
Same meaning. Stiffness, rigidity, all these things will have same meaning, right?
Okay. Strong.
Strong. Okay. Means this number is going to decide the strength of the system with respect to stability.
Okay, sir.
That is very high. I can say the system is very strong to accept the small disturbances.
Okay, sir.
Any other doubt you have?
No, sir.
Jagdish Kumar. Jagdish Kumar. He is not there. Dinesh. Dinesh.
Yes, sir.
Dinesh. Tell me.
Sir, we use this midpoint compensation for increasing our Pmax, sir, right?
Yes.
Sir, then why we in last problem take sir Pmax low? 4 by means in second region the Pmax hour is very high, na, sir. 4
That's
times.
what I explained till now, right?
Not getting, sir.
See, this one side you get let's say 9 per unit as a Pmax. This number I have calculated, this side number.
Yes, sir. 9. Or
I got this number 9. I got this number 3.
Yes.
Okay, based on what value we have to keep the loading? Is it 9 per unit or 3 per unit?
Sir, if our Pmax is maximum, then it is 9 per unit.
Okay, 9 per unit. What is the necessity of calculating P maximum? Why we have to calculate P maximum?
To keep our load on the
Load. Yes. So if you select Pmax as 9, can we keep power flow as 8 per unit?
Yes, sir.
Because it is less than 9, right?
Yes.
If you are keeping the power flow as 8, it is crossing the first P maximum, right?
Yes.
Then system is unstable.
Okay.
See, that's what I said.
Okay, sir. Getting it. Thank you, sir.
Okay.
Okay.
Any other
Sorry.
doubt you have, Dinesh?
No, sir. Thank you.
Jagdish Kumar. Jagdish Kumar.
Hello, sir.
Tell me, Jagdish.
Sir, in the ending problem, you said the sharing of reactants based on the source.
Yeah.
Sir, can we simply say that which side has higher reactance is the
That's the
correct
final.
answer?
That's the conclusion derived from this only, right?
Okay, sir.
So why you are selecting higher reactance?
That doesn't mean, sir. While dividing the reactants, here in first case there is no sharing. In second case, equally divided. In third case, we divided 3x by 4 and
Why?
3 by 4 and 1 by 4.
Why?
Based on the source, sir. That means.
Because he said 75% length is keeping source.
Yes, sir.
Okay.
That I mean
okay.
that.
See, Jagdish, length is reactance value proportional to length only, right?
Yes, sir.
For a L length, if you have X reactance.
Yes, sir.
L by 4 length, how much reactance you have? X by 4.
Yes, sir.
That's it. That's what we have done here.
Okay, sir. And
This
that
is
I mean, which side has highest reactance? That side power flow is low.
That side Pmax will be less, not power flow.
No, Pmax will be less.
Pmax will be low.
Yes, sir.
Based on that value only, we have to keep the loading.
Okay, sir.
Okay.
Okay, sir.
Any other doubt you have, Jagdish?
No, sir.
Yeah. Suryan. Yeah.
Sir.
Tell me, Suryan.
Sir, whether we can say the synchronizing power as a coupling strength of rotor, sir.
Synchronizing power as?
Coupling strength, sir. To maintain coupling strength, we have to consider the synchronizing power.
Okay. Okay.
Sir, I'm asking that in that way I can take it, sir. Sir, for methods to improve steady state stability.
Methods to improve the steady state stability. See, if synchronizing power coefficient number is very, very high, that is an indication of accepting the disturbances, right?
Yes, sir.
How you are saying the system is stable or unstable? Depending on dP by d delta only.
Okay, sir.
The point where you are standing, at that point, if dP by d delta is very, very high, what's the meaning of that? That system is capable to accept the small disturbances. After accepting it, it is capable to come to stable mode.
Yes, sir.
So that highest value, if we have, then we can say system stability is more under steady state.
Okay, sir.
Any other doubt you have, Surya?
Sir, another one general doubt in fault analysis, sir.
Tell me.
If we have the star ungrounded systems, we have take that in LG fault, the fault current value is 0, no, sir.
Fault current value is 0, yes.
Yes, sir, but by the concept of network, I am understanding, sir. But by physical significance, I can't get it, sir.
No current flow, Suryan. You don't have closed path for current flow, right?
Sir, in that case also, in star grounded also, if the both cases are grounded, there is no physical connection, no, sir. By
Physical connection
assuming
is there
that,
by ground. Physical connection is there by ground, right?
sir, but we are considering only as the virtual shot, no, sir.
Ground, we are not considering that as virtual shot on the paper. We have physical connection by ground.
Okay, okay, sir.
If ground is an insulator, there is no issue for us, right?
Yes, sir.
Ground is a good conductor of electricity, right?
Okay, okay, sir. Got it.
Okay.
Okay, sir.
Yeah. Any other doubt you have, Suryan?
No, sir.
Yeah. Chamotkar. Chamotkar.
Hello, sir.
Tell me.
Sir, slide number 60.
Okay.
Sir, here this second graph dPe by d del. Sir, that portion we have said as stable. So, sir, that we have copied means taken the points directly from above graph.
Above graph.
Okay,
Above
so sir,
graph, see. In above graph, why you are saying minus 90 to plus 90 as stable?
sir, because the slope is positive.
Slope we have drawn in the second one, right?
The slope is taken from the first one. Okay, yes, okay, drawn.
Now drawn slope. If slope is positive, then the system is stable.
Okay, yes, sir.
Yes.
So, okay, from minus 90 to 90. And sir, that STATCOM is equivalent of no load synchronous motor.
Yes.
Okay, sir. Thank you. Thank you.
Sai Charan Reddy. Sai Charan Reddy. You have any doubt? Sai Charan?
Hello,
Sai
sir.
Charan. Tell me, Sai Charan.
Sir, in midpoint compensator, it will increase the Pmax, but conditions are we should, if you want to obtain
Practically, it
maximum
may not be
advantage-
double. Practically, it won't make it double. Sai Charan.
So if we want to obtain maximum power maximum, we should keep it in midpoint.
Midpoint, yes.
Okay, sir. Sir, in rigidity, you gave a definition at first about that reliability, na sir.
Okay, reliability.
We can assume that this rigidity is indirectly the reliability.
No. Reliability is a different definition.
That confidence of
Reliability is a different definition. Rigidity is a different definition. Reliability means confidence. Rigidity means strength.
okay, sir.
Okay,
You
Sai
gave-
Charan.
I thought that this definition would be that only.
No. Those two are different.
Okay.
Any
sir.
other doubt here?
Sir, can you give a definition for this also, sir, like reliability?
Reliability.
Yes, sir.
Already we defined, no, it is a confidence level of system of satisfying the load demand.
No, sir.
For all the time.
For the reliability, can you please give for the rigidity also?
Rigidity is the strength of system in accepting the disturbances.
Sir, here only I am confusing, sir. In accepting the disturbance means in that also it is accepting the disturbances, no, sir.
That reliability is different. It is simply it is the strength of the system of accepting the disturbances. What we said in case of reliability, it is a capability of system of supplying the load all the time, irrespective of the disturbances.
So it is resistive to the disturbances only, no, sir, indirectly. It is supplying the load all the time means even the disturbances come also, it will supply the load means it is resistive to the disturbances, no, sir.
Not resistive to disturbances. It won't oppose a disturbance. Won't oppose a disturbance. Even though you have a disturbance, but still by some way the system is capable to supply the power. It's not going to oppose the disturbance, right?
Okay, sir. Okay, sir.
Getting Saijaran?
Yes, sir. Yes, sir.
Yeah. Any other doubt you have?
No, sir.
Yeah. Proceed.
హలో సార్
Tell me those.
సార్ 60F లో అదే కర్వ్స్ ఒకసారి డౌట్ సార్ పైన -90 నుంచి +90కి తీసుకున్నాం కాబట్టి కింద కూడా అవే తీసుకున్నామా సార్ లిమిట్స్?
Why you have taken -90 to +90 first case?
ఇంక్రీజింగ్ అంటే పాజిటివ్ స్లోప్ ఉంది కాబట్టి స్టేబుల్ ఉంది సార్.
What you have drawn in the second one, second curve?
సెకండ్
What is the second curve you have drawn?
అదే సార్ DPE by D delta.
Slope itself you have drawn there.
ఎస్ సార్.
If that is positive, then the system is stable, right?
ఎస్ సార్.
Is DPE by D delta value positive? Obviously in the range of -90 to +90 because it's a positive curve.
Because it
Really?
is sir, I didn't get that sir. I didn't get that.
Why you have said -90 to +90 in the first case?
సార్ ఇంక్రీజింగ్ గా అవుతుంది అని చెప్పారు కదండి సార్ ఒక ప్రాబ్లమ్ లో మనం
Slope.
ఇక్కడ స్టాండ్
Slope. What
స్లోప్
you have
సార్
drawn in the second curve?
డిపి స్లోపే డ్రా చేసాం సార్.
Slope you have drawn. Means if
Yes,
DPE
sir.
by D delta is positive, then the system is stable.
ఎస్ సార్.
From -90 to +90, you have a positive value, right?
ఎస్ సార్.
Then obviously it is a stable region.
ఓకే.
Then what's the doubt you have?
No sir. I thought that so from -90 it is increasing, from 0 onwards it is decreasing like that I thought.
That is DPE by D
got it.
delta change. It is, that's it.
Okay, got it sir. Sir in 61F sir. Sir 30 degrees to 45 degrees అది ఒకసారి ఎక్స్ప్లెయిన్ చేయరా సార్? అప్పుడు నేను
See, if you keep the angle very close to 90, for example, 90 is the stability angle you have considered, right?
ప్రీవియస్ గ్రాఫ్ నుంచి ఒకసారి ఎస్ సార్.
Okay. So if you take 85 degrees, system is stable or unstable? Delta.
స్టేబుల్ ఓన్లీ సార్.
Stable. But 85 degree, if you take, the power flow is very close to P maximum, right?
ఎస్ సార్.
Now, if there is a small disturbance you create continuously,
ఓకే సార్.
then there's a chance to say the system may lose the synchronism.
ఎస్ సార్.
Yes or no? So
yes, sir,
if you
yes,
are keeping the angle very close to 90 degree, even though you say the system is stable right now, it may become unstable maybe after some time.
ఎస్ సార్.
Following. Now, how much angle I have to keep? Low angle. Even lower angle we have to keep.
ఎస్ సార్.
Let us take 60 degree.
ఓకే.
If you take 60 degree, the power flow is very less compared to P maximum. System is having
yes.
good stability. Under steady state means for small disturbances.
ఎస్ సార్.
But if there is a large disturbance on the system,
ఓకే.
then
Then
the
the
system
system
will
may-
lose the synchronism.
ఎస్ సార్.
What's your aim actually here? We have to set the operating point in such a way that the system should not lose the synchronism for any type of disturbance you keep.
ఎస్ సార్.
Either it is a small disturbance or high disturbance, whatever it is. Your system should not lose the synchronism such that we should create the initial operating point.
ఎస్ సార్.
Okay. Then to maintain that very high stability for the system, delta equals to 0 degree you can keep, right? System will be well stable.
ఎస్.
But why you are designing line and all? You have the power flow, not to maintain stability first.
Sir?
If you keep delta equals 0 degree, you don't have power flow at all.
ఎస్ సార్. నో పవర్ ఫ్లో. ఎస్.
But delta equals 0 degree will give good stability for the system, right?
But we okay sir. We want to have power flow.
We want to have power flow. That's why we have designed the line, not to maintain the stability. Yes or no?
Yes. Yes sir.
So to maintain good stability as well as good power flow, it is compromised to keep the angle in this range, 30 to 45 degrees.
Okay. Okay sir.
Understood?
Yes sir. Understood sir. No.
Yeah.
Sir,
Yeah,
next
okay. Tell me.
yes sir. Steady state stability limit to synchronizing state ఉన్నాయి కదండి సార్ అవి. అప్పుడు మామూలుగా మనము స్టడీ స్టేట్ అదే కదా సార్ మనకి మాక్సిమం పవర్ రావడానికి తీసుకుంటాం 1 minute. మెథడ్స్
How you
ఇంకో
say,
చెప్పండి.
how you say system is stable or unstable based on what?
సిస్టమ్ ఇస్ స్టేబుల్, స్టడీ స్టేట్ స్టెబిలిటీ లిమిట్.
Just based on P maximum, can you say system is stable or unstable?
నో సార్, we won't
Based on
have
what
other
you tell? Based on what you tell whether the system is stable or unstable. dp by d delta ఉంది, right?
ఓకే. స్లోప్ అని తీసుకోవచ్చు సార్ అప్పుడు దాన్ని.
Slope. Slope.
Okay.
dp by d delta is slope only I have written there.
ఎస్ సార్, ఎస్ సార్. నో
If that value was very, very high, obviously system stability is more, right?
ఎస్ సార్.
Hmm.
85 ఎఫ్ సార్.
Okay.
సార్ అక్కడ ఎక్సెస్ ఎందుకు సార్ మనం లో తీసుకున్నాము అది అర్థం కాలేదు.
Naturally, that transformer, you have a coupling transformer between STATCOM and line. That coupling transformer will have very, very low reactance.
ఓకే సార్.
So if it is not negligibly small, you can get some number here, very low number you are going to get.
ఓకే సార్.
After saying that it's a very low number, so you don't get the P maximum value double. You don't get 2 times
yes.
P maximum 1. You may get 1.8 times, 1.6 times like that.
ఓకే సార్.
As it's a theoretical study, I am saying it's double. Practically speaking, you don't get double.
డబుల్. ఓకే సార్. ఇన్ 38 ఎఫ్ సార్.
Okay.
సార్ మూమెంట్ ఆఫ్ ఇనర్షియా అది ఒకసారి ఎక్స్ప్లెయిన్ చేయండి.
We will discuss that in fault stability, transient stability later. Weight, for time being, you feel weight. Volume
Okay.
of the rotor, weight of the rotor.
ఓకే సార్.
Okay.
సార్ మెథడ్స్ లో ఇంకొక డౌట్ ఉంది సార్. అక్కడ ఇప్పుడు మామూలుగా నిన్న డిస్కస్ చేసిన ప్రకారము డెల్టా నాట్ డెల్టా 2 ఈక్వల్ అవ్వవా సార్ మనకి?
Delta is a variable angle.
yes.
For example, if you have a function like x plus x square plus 2, that x is a variable, right?
ఎస్ సార్.
Delta is a variable number.
ఓకే సార్. డెల్టా
Like
నాట్
delta
లో.
naught, delta 1, delta 2, these are numerical values.
ఓకే.
Delta naught is a numerical value. Delta is a functional value.
అది ఎలా డిక్రీజ్ అవుతుంది సార్ మనం లోడ్ తక్కువ వేసినప్పుడు?
Delta naught, we said no. Whenever you are decreasing load, obviously you are saying power flow is less.
ఎస్ సార్.
Power flow is less means sin delta will be less, right?
ఎస్ గాట్ ఇట్.
This delta angle, operating angle will be low.
Low.
Okay.
థ్యాంక్ యూ. గాట్ ఇట్ సార్.
That's it.
దట్స్ ఇట్. థ్యాంక్ యూ సార్.
Bharat.
Sir, in transmission line, I have observed one thing that each phase consists of 2 lines which run along with each other with a small gap between them. Is that what?
That's a bundle. That's a bundle conductor.
Double line, sir.
That's not double line. It's a bundle conductor.
Bundle conductor.
Bundle.
But bundle means there will be more than 2, no, sir? Bundle means
More than 2 conductors in each phase, but
then
very close. Very close.
What is double circuit line, sir? Obviously,
Double circuit line means running 2 3-phase circuits on same tower.
2 3
2 3-phase circuits on same tower.
Oh, so a tower consists of 2 sides, so one with the cross arms.
Yes, like this.
So there are both double circuit line
This
and
is one 3-phase circuit on one side, and it's another 3-phase circuit. This is called as double circuit line.
This is double circuit line.
now,
Bundling means
now listen. Now, in place of one conductor, if I keep 2 conductors,
that is bundling.
that is bundle.
Okay, so got it.
Now, if
That
you
is,
keep the same bundle on the other side, it's a double circuit line, bundle conductor, double circuit line.
Yeah.
This side also, if you keep 2 2 or 4 4 or 6 6 according to the requirement, then it will be bundle conductor, double circuit line.
Okay, so got it. So double circuit line and parallel lines both are same.
Parallel line means we have a small minute difference in the definition. Sthiti. Parallel line is one circuit on one tower, other circuit on the other tower configuration.
Okay. Okay,
For
sir.
example, if it is a generator, we have generator. From this one, two circuits are starting. Okay, this is running on one tower configuration completely,
Okay. Okay, sir. Okay.
and this is running on other tower configuration.
Okay, sir. Got it.
But both are ending to the same bus bar at the end.
Yes, sir.
Then these two are called as parallel lines.
Parallel
And the
lines.
distance between these two is very, very high.
Yeah, yeah.
Okay, by that way, we can neglect the mutual linkages between these two.
Yes.
That is called as parallel line.
Okay, sir.
You can ask me that double circuit line is also parallel line only.
Sir?
Double circuit line
That's
is
parallel
also
line, but
line.
there will be
But
mutual.
there will be mutual linkages.
Yes.
Minor difference. You have to observe.
Okay.
Okay.
One more doubt is, so we prefer to operate in 30-degree and 45-degree range now.
That's what I explained just now.
Yeah. Okay, sir. I got it.
Have you listened it?
Yes, sir. I listen.
Yeah.
So there will be one more line, sir, on top of this tower. What is that?
That's a
line?
ground wire. Ground wire or you say earth wire for the lightning protection.
Lightning protection.
Whenever the lightning strike occurs, to avoid fall of the lightning stroke on the power conductor directly,
that line will absorb
that dummy wire.
Okay.
Completely useless wire in steady state operation.
Okay, that's not
That
related
is like
to
a
this.
protection. That's like protection to the power network from lightning strokes.
Okay, thank you, sir. That's it.
Bharati.
Hello, sir.
Tell me, Bharati.
Sir, initially we derived two conditions for maintaining P max, no, sir. Del is equal to theta and x equal to √3r. In that, like my doubt is, my understanding is like del is equal to theta is to get the maximum power. Like for example, if it is 10 megawatt, then x is equal to √3r is to increase that maximum power with respect to x. Like
Okay.
X example for 215 megawatt. Is it right, sir?
See, for example, you have one system like this. Okay. And this voltage magnitude is 1. This voltage magnitude is also 1.
Okay.
Okay. And we have some resistance value 0.1 and the reactance value, let's say 0.3.
Okay, sir.
We have some mod z value here, which is root of r square plus x square. And you please tell me what is that magnitude and angle?
What, sir?
What is that magnitude and angle? Magnitude and angle.
Magnitude.
Check.
1 minute. .3162 magnitude.
0.3162 magnitude. Okay. Angle?
71.56.
71.56. Are you getting this one? It is Pmax of that network. Delta equals to theta I have maintained.
Okay.
So x equals to √3r. X equals to √3r is not maintained.
Yeah.
This is mod v1 mod v2 by mod v.
That is
mod
Pmax.
z minus mod a by mod b. Mod v square means mod v2 square into cos of theta minus alpha. Alpha is 0. How much is this? You tell me P maximum. .162.
Yes, sir.
162 per unit. Okay?
Yeah.
It is only with delta equals to theta. Now,
Okay, sir.
same network, draw like this. I kept a capacitor also. Okay.
Okay, sir.
Mod V1 1 per unit, and this is 1 per unit again, voltages. Now, in this case, I am maintaining delta equals to theta as well as x equals to root 3 are both.
Okay, sir.
Then resistance value will be as it is 0.1 only, but reactance will come to be root 3 into 0.1.
Like the sum we did.
Yeah. A capacitor is there that will manage to make this number as this value. So it's 0.1 plus j 0.1732. It will happen.
Okay, sir.
The Z new after making the modification.
Okay.
Okay, what is the Pmax new value here after maintaining both conditions? Mod V square by 4R, right?
Yeah, yes, sir.
V square means 1. 4R is how much? 0.1. How much is this number? 0.5.
0.2.5.
Earlier, how much you got? Without maintaining x equals to root 3R, you get this number 2.162. But after maintaining x equals to root 3R, along with delta equals to theta, you got 2.5. But this theta is restricted to 60 degree now.
Yes, sir. Yes, sir.
In the previous case, what is theta? 71.56 degree.
Yeah, yeah.
That's the difference.
Sir, can we comment on stability margin if P max increases, or the stability margin depends on the given system conditions?
What is the formula for stability margin?
P max minus.
That's it. You are saying directly it depends on Pmax.
Yeah. Okay, sir.
Pmax is changing, definitely stability margin will change for a given power flow.
Okay.
A given power flow. For example, power flow is 50 megawatt. Pmax is 120. Then what is stability margin? 70. 120 minus 50.
Yeah.
Power flow is 50 only, but Pmax I increased to 150.
So margin will increase.
Stability margin was increased to 100.
Yes. Okay, sir. I understood.
Yeah.
Thank you, sir.
Vaishnavi.
Sir, in 86 of page number, sir.
Okay.
Sir, in this not you told here only, sir. Ikkada Thevenin is Thevenin voltage equal to mod Vm delta by 2 annar kada sir. Enduku mod V of delta avaguddu sir adi.
No, is midpoint voltage equals to source voltage, right? Midpoint voltage is nothing but source voltage only. Because its excess is very low, we said, right?
Yes, sir.
By saying that excess is very low, obviously the source voltage and midpoint voltage are equal.
Yes, sir. అంటే ఇప్పుడు థెవెనిన్ నెట్వర్క్ అనేది అక్రాస్ మిడ్ పాయింట్ కి గ్రౌండ్ కి మధ్యన కన్స్ట్రక్ట్ చేస్తున్నాం. ఓకే సార్, చిన్న స్మాల్ డౌట్ సార్. సిస్టమ్ సింక్రనిజం లో ఉంది అంటే మీనింగ్ ఏంటి సార్? నాకు అది అర్థం అవ్వట్లేదు సార్. సిస్టమ్ లూజెస్ సింక్రనిజం అంటాం కదా సార్. అదే సార్ డౌట్. సింక్రనిజం అంటే మర్చిపోయాను.
Do you have many synchronous machines in your system?
Sir?
Do you have many synchronous machines in your system?
Where, sir?
In the power system network, practically, can I say we have many synchronous generators?
Depending upon the capacity, if you want.
You think about Indian power system, Vaishnavi.
Yes, sir.
In Indian power system, do we have only one single generator or many generators?
No, sir. No, sir. More, we have many, sir.
Many generators.
Yes, sir.
See, according to the generator speed, generator rotor speed, it will induce a EMF at certain frequency.
Yes, sir.
If the synchronous machines are not rotating at same speed,
yes, sir,
definitely frequency of the induced EMF will be different from one machine to other machine.
Yes, sir. It will.
Then we say machines are not properly synchronized.
Okay, sir.
If the frequencies of the machines are equal, frequency of the induced EMFs are exactly equal, we will say machines are properly synchronized.
Okay, sir.
Okay.
Sir.
Nearly equal. Nearly equal also it will compromise it.
The systems are in synchronism.
Because continuously we are operating the system with disturbance only, right?
Yes, sir.
Disturbance only means it's not possible to maintain the frequency exactly 50 hertz all the time.
Yes, sir. Yes.
For all the synchronous machines, definitely frequencies are varying, but the frequency variation was limited to very low number.
Okay, sir.
If it is limited to very low number, then I can say, okay, it's adjusting and it is a bit synchronized.
Okay, sir.
Okay.
Okay, sir. Understand, sir. Sir, ఇంకొక స్టడీ స్టేట్ స్టెబిలిటీ అంటే చేంజ్ ఇన్ పిఈ బై డెల్టా అనా సార్, లేకపోతే పిఈనా సార్? అది
what steady state stability? Studying the stability for small disturbances.
Okay, sir. Steady state stability limit means
Pmax.
Pmax.
That's it.
Steady state stability means P maximum. Steady state stability means dp by d delta, sir.
I was saying both steady state stability. Tell me, what is P maximum name?
P maximum steady state stability limit, sir.
dp by d delta?
Steady state stability.
dp by d delta is synchronizing power coefficient, not steady state stability.
ఓకే సార్, ఓకే సార్. అంటే రెండు ఒక ఏంటి సార్? హలో సార్, ఒకసారి మళ్ళీ చెప్పరా సార్? అది
కాదమ్మా, dp by d delta synchronizing power coefficient.
Yes, sir.
If that is maintained as high, I will say system stability is high. Adi meaning akkada.
Okay, sir.
మీరు అట్లని dp by d delta ని steady state stability అని పిలిస్తే అసలు మీనింగ్ ఉండదు ఆ స్టేట్మెంట్ కి.
అంటే క్లాస్ లో క్వశ్చన్ అండ్ ఆన్సర్స్ లో అంటే మీరు చూసి చెప్తా ఉన్నారు కదా సార్, అక్కడ డౌట్ వచ్చింది సార్. అని
వాట్ ఇస్ సింక్రనైజింగ్ పవర్ కోఎఫిషియంట్?
సింక్రనైజింగ్ పవర్ కోఎఫిషియంట్ ఇస్ Pmax cos delta, sir.
Okay, that is dp by d delta is synchronizing power coefficient.
Yes, sir.
Okay, what is steady state stability limit?
Pmax into sin delta.
Pmax, that's it, Pmax.
Sorry, sir.
Steady state stability limit is P maximum.
Yes, sir.
What do you mean by steady state stability of system? Maintaining stability for small disturbances. ఒకటి ఏంటంటే డెఫినేషన్, ఈ రెండు ఫార్ములాలు.
ఓకే సార్, ఓకే సార్. సార్ మళ్ళీ సింక్రనైజింగ్ పవర్ ని మనము సెన్సిటివిటీ ఆఫ్ ద పవర్ అని కూడా చెప్పొచ్చు కదా సార్? అంటే ఇట్ ఈస్ ద చేంజ్ ఇన్ పవర్ డెవలప్డ్ బై ఆల్టర్నేటర్ ఫర్ స్మాల్
sensitivity also.
Okay.
Real power sensitivity with respect to angle.
Okay. Okay.
Ena?
Okay. Okay, sir. Clarity వచ్చింది.
Doubt unma?
No, sir.
Imtiaz Pasha.
Good evening, sir.
Good evening.
Sir, I have just some clarification in x is equal to root 3r, sir.
Okay.
Sir, x is equal to root 3r means if we get the P maximum at that time, sir. If x is equal to root 3r means the stability will be and go unstable at that time. Can we say?
No, you say Pmax is high in the sense you say simply stability is 1%.
Yes, sir. If we behind x is equal to root 3, can we say the system will stable, unstable?
That you can't say, right? X is more than root 3 or x is less than root 3 or is not a condition to say system is stable, right?
This is only for the Pmax.
That, see, why you are calculating that x equals to root 3r and all?
Sir, we have two statements, sir, condition for the Pmax.
That's okay. Yeah. Why you have gone for x equals to root 3r condition? You tell me.
For getting the P
Why we have
maximum.
done it?
For getting the P maximum.
Just read the statement where I have written it. X equals to root 3r we have written at some place, right? Just look at and read it once. See the screen, what I have written there.
For non-linear.
Mm-hmm.
Condition for maximizing the Pmax will be.
Maximizing P maximum is a aim here. It's not P max.
Okay, yes, I forgot that maximum step.
This is your P maximum.
Yes, sir. Yes, sir. Sir, one more is there.
Tell me.
Sir, in per unit, I'm confusing some point, sir. Sir, can you open that problem, sir?
Which problem?
There is a 11 kV 500 MVA.
Okay.
In the transformer is 0.2 per
Okay.
unit.
Tell me, what's the doubt you have on that?
Can you open that? This one, sir. Sir, I'm confusing. The same problem is there in workbook, sir. Is given XT is equal to 1.09 ohms, sir.
XT.
Yes, sir. XT is equal to 1.09 ohms. And rating is the 11 by 6.6 kV.
Okay.
I take the base value as a 11 kV and 20 MVA. Some base 20 MVA. At that time, how can convert the to per unit, sir? Because there is a star and
only
delta.
have to tell. That you only have to tell the Imtiaz. That you said 1.09 ohms, sir.
Yes, sir.
On what site it is?
Anyone,
On
sir.
what side?
Primary.
Is it on primary or secondary?
It's primary, sir.
Is it given in the problem?
It's not given direct. It's given that.
Not given means how you take on primary 1.09. If you take primary, you get one answer. If you take it on secondary, you'll get a different answer.
Sir, I'm getting two answers, sir.
That's what I am saying. Yeah, there is a mistake in the question then.
Okay, sir.
Where you found that type of question?
Sir, in bits and bytes.
Okay. They might have given, I think so. They might have given on which side. They should give, strictly speaking, on which side it is. You read that question once, I will tell you if you have not.
Okay, sir. A fault occur at F in network shown figure. Data about the system. Generator is given 2 MVA. Reactance is 2.18 ohms solidly at where transformer T1 is 2 MVA, 6.6 per 11 kV. Reactance is 1.09 ohms. The line reactance is 0.5 ohms at 11 kV.
Okay.
And T2 is same as the T2 is 2 MVA, 11 by 6.6 kV. Reactance is 1.09 ohms. It's not mentioned any side, sir.
They have to mention. I think it may be a printing mistake.
Okay, sir. Just I'm confusing that.
They have to mention. Strictly, they should say on which side it is.
Okay, sir, one more is there, sir.
If they don't say that, you will get two answers.
Yes, sir, I'm getting one side 11 kV and 6.6. There are two different answers.
Yes. Okay.
Sir, one more.
Tell me.
Sir, can we say generator have a small generator can have more short circuit MVA?
Small generator. What is it meaning?
Means have small rating of the generator. Can we say it have more short circuit MVA rating?
We can't say. Without knowing its reactions and all, we can't say, right?
But there is a one problem, sir. They are given 3 short circuit ratings, sir. 1500 MVA, 1200 MVA, 1000 MVA. Yes, sir. Fault is occurring at the bus.
That we'll discuss in JetBus later. JetBus. Bus impedance matrix we have no.
Oh, okay, sir.
In that one, I will try to tell that question. You ask me again after completing JetBus. You ask me doubt. That question.
Okay, sir, one more. I'm confusing in some terminology, sir. Could you tell me? Sir, there is a statement as each has reactance to positive sequence current of 5%. What it means, sir?
Yes.
Each has reactance to positive sequence current of 5%.
Means the positive sequence reactance is 5%. That's it.
Means x1 is equal to
0.05.
0.05. Sir, I am taking same as but getting wrong answer. Sir. Is given in answer is some. I didn't understand that terminology.
You send me the question and the solution. I'll see.
I sent sir already.
Okay, I will see. I will see one. Just to make a reminder to me, I will check once and I will come to you.
Oh, okay, sir.
Any other doubt in there?
No, sir. Thank you so much.
Correct.
Sir, good evening, sir.
Good evening. Tell me, sir.
Sir, I'm having some normal general doubts. Sir. What was the purpose of keeping the reactor in substation?
Reactor?
Yes.
Which reactor?
Means I went to substation. There I seen reactor. Sir. Means I asked them that they told to supply reactor power, we'll keep the reactor in substation.
What's the rating of that substation?
400 kV.
400 kV. Then it's okay. It's a shunt reactor. Shunt reactor, right? Shunt or series?
I think, sir. Means I went long back, so 1 year ago.
It is a shunt reactor to reduce the Ferranti effect.
Current effect.
Correct.
Sir,
To reduce Ferranti effect, they will be keeping the shunt reactor, not to supply reactive power, strictly speaking.
Okay.
To control the Ferranti effect, they will keep the shunt reactor.
Okay, sir. Okay. Only for that purpose only, they will keep that reactor.
400 kV bus bar. 3 reactors you observe: phase A, phase B, phase C.
Yes, sir.
We might be connected with star or delta. Might be star, I think so. Star solidly grounded.
Okay, sir.
Maybe I think 40 MVA reactor, 40 or 50 MVA reactor.
Okay, sir. Okay, sir. Got it, sir. Thank you, sir.
Yeah. Anil Kumar Malhotra.
Sir, good evening, sir.
Yeah, please tell me.
Sir, in 87F.
87.
Yes, sir, 87.
Okay.
So V Thevenin, sir, we have calculated sir, that one.
V Thevenin.
Sir.
Okay. The derivation I have not discussed, Anil Kumar. Complete derivation I have not discussed. For time's sake, I said simply V Thevenin is VM.
Okay, sir.
Okay. Here we have some more thing to discuss about that V Thevenin.
Okay, sir.
Okay.
Sir,
if you want that whole derivation, you get this textbook once. Power system, dynamics and control.
Yes, sir.
By K.R. Padiyar. In that one, the derivation is there. If you want, you can go through it completely.
Okay, sir. Okay. Sir, yes, sir. Sir, in 45, please come, sir. 47.
47.
Yes, sir.
Page number 47, you are saying?
Yes, sir. Yes, sir. 47.
Okay.
Sir, in this, how we can conclude that non-linear, sir? P max.
The denominator we have x square, right?
Yes, sir.
It will be non-linear only. If you draw the P max with respect to x, it will come to be non-linear only.
Okay, sir. Okay.
Okay?
Yes, sir. Okay, sir.
Clear now?
Thank you, sir.
That's it?
No, sir. Yes, sir.
Anybody have doubts? Please raise your hands quickly.
Sir, Imtiaz.
Tell me, Imtiaz.
Sir, for example, అంటే ఒక క్వశ్చన్ లో ఏమి ఇస్తారంటే పాజిటివ్ సీక్వెన్స్, నెగటివ్ సీక్వెన్స్, జీరో సీక్వెన్స్ ఇంపిడెన్స్ రియాక్టెన్స్ ఉన్నప్పుడు Hello.
Tell me.
Sir, if the question gave positive sequence, negative sequence, and zero sequence impedance, they indirectly said, call that the fault, find the fault, find the voltage in the healthy phases where other two phases are in faulty phase. Can we consider as a double line fault?
It may be double line or double line to ground also.
Means which will we prefer more, sir? Double line or double LG?
I can't decide it. There simply two phases are faulted and one phase is not non-faulted. Two phases are faulted means which fault? Is it double LG or LL?
It's not given that's a clarity in that, sir.
That's again a problem.
Can we consider as a it's given as a zero sequence? Can we go to the double LG fault?
I can assume that zero sequence they have given extra to confuse us.
At that time, what will choose, sir?
They will give clearly in the question. Don't bother.
Okay, sir.
You do for your practice. You do LL and LLG both. You do for your practice.
First I do LL, sir. It takes 5 minutes time. I check the answer. There is no one
No
option
problem.
in that.
No problem. India,
Then
as we are in the listen. As we are in the learning stage, we used to get this type of questions sometimes. Okay,
sir.
But you see previous gate question. Is there any ambiguity in the previous gate question? Anywhere? No.
Still I did not check, sir.
I'm saying in general.
Okay, sir.
Okay. So if you are writing an exam, you don't get this type of ambiguity in the question asked in the examination.
Okay, sir.
But in practice, you may be getting these things. Okay, if you are getting this type of question, let us say, you enjoy it. Okay, I will do LL fault first, I will do LLG fault first, whatever the answer you give, I will do both. That's it.
Okay, sir.
Okay, for example, the same question asked me ESC prelims, for ESC mains exam. Okay.
Yes,
Then
sir.
I will do both fault analysis. LL fault I will do, LLG also I will do. Examiner will choose one of them.
Okay, sir.
Getting me what I'm saying?
Yes, sir. I am getting.
Yeah.
This one, sir. Okay. Thank you, sir.
That's it.
Yes, sir.
Any other doubts? You can raise your hands.
Hello, sir.
Yes, Ajay.
Sir, generally,
Yes, Ajay.
at the distribution Hello, sir.
Tell me, Sajid.
Sir, generally at a distribution transformers near our houses, there will be a GI wire coil, sir. To that pole, sir. GI wire coil. Is that earthing or what it is, sir?
Earthing.
Coil earthing.
Not coil.
Why they'll?
It's not coil earthing. It's simply GI wire earthing.
No, sir. There will be like a coil, sir, like inductor.
Is it on pole or ground?
Sir, through pole, wire, GI wire is at some part it is wound like inductor, sir, for same GI wire.
I'm asking you, is it on the pole or on the ground? Where?
Not above the pole, but near to ground, sir, on pole only.
Near to ground. Is
On
it
pole
connected
only.
to power conductor directly?
No, sir, it is left. It is left for a conductor. A rod is taken from the line, sir. A rod is taken from the line. For that rod, it is connected, sir.
Then it will be earthing only.
Yes, sir. But why it will be like inductor, sir?
Do you have that photograph?
Sir, tomorrow I'll send, sir.
Tomorrow you send.
Yes, sir.
Maybe for some support sake also they may twist that to pole sometimes.
Okay, sir. Okay. Tomorrow I'll send, sir, for confirmation.
Okay.
Okay, sir.
Any
Sir,
other doubts? Yeah.
sir, can we say symmetrical subtransit current also fault current?
In
AC
the
component
exam,
current.
if he's asking simply fault current, we have to give only AC component in the answer.
Okay.
If his interest is to know DC component also into the calculation, then they will ask that one clearly as asymmetrical current.
Okay, sir. Sir, fault currents of synonyms can be said that subtransient current, symmetrical sinusoidal current, AC
Symmetrical
component
RMS
current.
current, initial symmetrical RMS current.
Okay, sir. Okay, sir. Thank you so much.
Okay. Okay. Any other doubts? Raise your hands. Yes, we will close the session. Thank you. Pramod, I will inform you tomorrow. I have no information regarding offline classes. I will inform you tomorrow. I will inquire it and I will inform you tomorrow. Okay. Thank you.